All right, so we're continuing on. Again, what's potential energy?
Stored energy.
Stored energy. Very good. Within the realm of biology, okay, it's going to be stored in chemical bonds or in a concentration gradient of some sort. All right, so in this example, potential energy is stored in the chemical bonds of gasoline, transformed into kinetic energy by a combustion reaction, allowing the car to move. Okay, we're going to get into something called free energy. No, this is not the next liberal agenda. Everybody gets free energy. I'm kidding. Right? This is, in bioenergetics, it's the study of the amount of energy exchanged. Okay. We're also going to introduce a couple of different terms. We talked a little bit about them yesterday, endergonic and exergonic. I want you to think of those as pretty much the same thing as endothermic and exothermic. However, instead of talking about heat, because therm is heat, we're going to be talking about free energy. Okay? It gives free energy, it's the amount of energy available to do work, also known as usable energy. All chemical reactions affect G. That free energy, which is signified as G. So a change in G after a reaction is abbreviated as delta G. That triangle, it means change. So if you ever take, some of you might be taking physics, when you ever see that triangle, that means change. If it's delta V, it's change in velocity. This is delta G, the change in free energy. Okay. Here's the formula. Delta G equals delta H minus T delta S. Do not ask me what those mean.
How do you put
DELTA.
Well, no, is there a way I can type it?
Google.
Let me shades.
Wait,
Usually, sometimes there's shortcut
special
keys.
characters.
Yeah. I looked through the formula sheet. I don't think you have to know how to calculate free energy. If you ever take advanced chemistry, you will. All right. Delta H is the change in total energy of the system. T is temperature in Kelvin. Delta S is a change in entropy, energy lost to disorder. So if energy is released, delta G is less than 0. Okay? Meaning delta G is the energy of the entire system. So if we lost energy, we have less energy than we started with, and we would have a negative change. Think of it as like you're going 100 miles an hour and you hit that brake. Now you're going 80 miles an hour. You had a delta V, the change in velocity of negative 20. Okay. This would be like a negative delta G means you had a loss of energy equal to so many kilojoules or whatnot. So the products will have less free energy than the substrates. One thing I want you to pay attention to is y'all are very familiar with thermic, endothermic, and exothermic. Okay. Free energy is going to be the same concept, but instead of using therm, heat, we're using the word free energy. Okay. And instead of using the word exothermic, we're going to be calling it exergonic. Right? Because we're talking about free energy. And the reason is within the biological body, energy is not always stored as heat. Sometimes it's stored within chemical bonds, and this lets us do it that way. Have that discussion. These reactions are classified as exergonic if they release energy, so they have less energy than they started. Exergonic reactions are spontaneous. This is important. Okay? This is one of the things that makes them exergonic, is that they're spontaneous, meaning you don't have to keep adding energy for it to happen. It will happen on its own. Right? Okay. Now, that doesn't mean it doesn't have activation energy. It still has activation energy. It's just since the products have lower energy, less energy because it lost energy, it's kind of like having that rock at the top of the hill, that bicycle at the top of the hill. It is going to roll down on its own. Okay? You don't have to add anything to push it up. Right? That is what it means when it'll happen spontaneously. If you drop a rock on a hill, what's it going to do? It's going to roll down.
What about passive?
Say what?
Spontaneous and passive.
Spontaneous and what?
Passive.
Passive. You don't like passive transport or?
Passive, like it slowly.
So when we talk about it, so these can happen fast, they can happen slow. I don't think there's necessarily a delineation on exergonic reactions happening quickly. Because you can have exergonic reactions that are slow and take a really long time. Okay. What do y'all have over there? spontaneous reactions do not necessarily occur quickly. On that topic. With an exclamation point, I think that's important.
So they don't occur quickly? But why is it called spontaneous?
Spontaneous means it happens without you doing anything. Spontaneous doesn't mean quickly.
Oh.
Okay, for example, I might spontaneously decide to take my wife out to $100 steaks.
That's
It
not
could,
quick,
it
yeah.
could happen, but it might be 3 years from now.
Okay.
All right,
Why not just cook them?
that's what I prefer to do.
Yeah.
I'm just using an example. Jeez, come on.
$100 steak, that's a lot.
I'm 6'5". You want to know a secret? I've had multiple $100 steaks. You're just as likely to get just as good a steak if it's $20. Like nothing. So when I was in oil and gas, we'd go to these fancy places, take customers, and like half the time, like I'd get an $80 steak, and I was like, this is not very good. And it's like it was fancy. It's like, yeah, we did it with our special blend of spices and this that we did. I was like, no, this doesn't taste very good still. Like it's kind of bland.
Does it
So,
look cool?
Is
So
there
what?
an anniversary or something?
yeah, it looked cool. Although sometimes, one time it was an $80 steak, and the guy I worked with, he's like, and they came and they had it cut for you. And I just looked at it, and the guy I worked with, he knew me pretty well. He's like, never thought you'd pay $80 to $100 for a steak that was already cut up for you, huh? I was like, no. I was like, this is not me. But anywho, all right. So visually, this is what exergonic reactions are going to look like. Pretty much very similar to exothermic. Remember, delta G is negative, okay, because we lose energy. The hump shown in the free energy diagram is the reason. We'll discuss that soon.
Okay.
Suspense. Alright, so again, free energy, this is an example of an enzyme. We've got activation energy here that will be needed to start this reaction, but it proceeds down this hill. Products have less energy than reactants, so this is going to be exergonic. This one, is this exergonic or endergonic?
No, it's still extra because it's above the.
Yeah, it's still exergonic,
It's
right?
not very good.
Yeah, it's just not as big. Also, it's got what? Lower
Activation ratio.
activation energy. Okay, so if things have a lower activation energy, but they do not change the free energy of the reaction. So as you can see here, free energy is just the difference between the reactants and the products. And so the difference between the reactants and the products here is still the same. So the change in free energy between these two graphs is exactly the same. Okay, does that kind of make sense? Because it doesn't take into account this activation energy.
So did you have to do a test again?
Yeah, I did the juniors except for 2.
Sorry.
Where are y'all at?
Okay. Endergonic would be an uphill reaction. It requires energy. Exergonic is a downhill reaction. It's spontaneous and it releases energy. Y'all kind of follow that one pretty quick. Like I said, this is very similar to endothermic, exothermic. If a chemical reaction requires the input of energy, delta G is greater than 0. So that's kind of like if you're going 100 miles an hour, you add energy onto it, and then you're going 120, you had delta G, change of velocity of positive 20. This is the same concept, right? You're inputting energy, you're adding energy, so delta G, that change in energy will be positive. The reactions have more free energy than the substrates. These are classified as endergonic. Kind of like endothermic, these will be endergonic. So think that G in the gonic as G meaning free energy. They absorb that free energy. If we look at them graphically, it's going to look like this. Delta G is greater than 0 because the energy increased. Energy isn't added, so our products have more free energy than our reactants. This reaction is not spontaneous, right? This is the equivalent of having to push that rock up that hill the whole way. Okay.
So endergonic is not spontaneous.
It's not spontaneous. No, ma'am. All right, so we've got these two reactions. Which one is exergonic? No, we did anabolic,
It's the
catabolic.
bottom one. Yeah, top one. It's going to be exergonic. Why?
Endergonic?
I think it's the bottom one because it's releasing. It's
Breaking
breaking them up.
bonds. Yeah.
Yeah. Oh yeah, because I don't have to. Yeah. I know.
Okay.
You got it.
That's a nice way of saying yeah, I was wrong. Yeah, this one down here is going to be exergonic because you're breaking that apart. Now, when we talk about exergonic, catabolic reactions are going to be exergonic. Okay, so if you're breaking stuff down, you're releasing energy in some way, shape, or form. Kind of like we break down glucose, that's a catabolic reaction, so it's exergonic.
So exergonic
And then say what?
exergonic is catabolic.
Yes. So what's this type of reaction up here then?
Anabolic, so it's
Exerg.
gonna be
Exerg. Endo.
Nope. This one up here.
Yeah. Endogonic.
Endergonic, anabolic. Because we're putting stuff together, building stuff.
Is
And
the only
again-
difference-
Say what?
is the only difference where the plus H2O is?
Yeah, so this is actually the same reaction. It's just one's going this way and one's going this way. So, ooh, yeah.
It's like photosynthesis and cellular
All right.
respiration.
See if you can get this. What is this reaction called, and what is this reaction called? We went over it here.
Photosynthesis
Oh,
and
nope.
cellular
It is-
Irreversible?
Nope,
Reversible?
nope,
Irreversible.
no, wrong thing.
Activation.
All right, what is this?
That's H2O.
Okay.
What is it, combustion?
Oh, it's
Activation.
No, it's combustion.
No.
hydrolysis.
Hydrolysis?
Hydrolysis.
Hydrophobic?
No, this is
No.
hydrolysis right here.
Wait, hydrophilic.
No, hydrolysis and
Dehydration.
dehydration synthesis.
Yeah.
Okay. So synthesis means putting together, and we're taking out of water, so we're dehydrating this. Dehydration, taking out the water. Synthesis, putting it together. Hydrolysis, you're breaking apart a water, and you're breaking apart the molecule. Lysis means to break apart. Hydro means water. And again, when we talk about like biological molecules, in general, that's pretty much how they're all broken apart or put together when you're building them or breaking apart a polymer. If you break them apart, it will be hydrolysis. If you put them together, it will be dehydration synthesis. Now, they might have specific names for that within that molecule. Like in proteins, it'll be called a peptide bond formation or something like that. But essentially, it's going to be the same thing. Like you're adding water to split stuff out, or you're taking water out to put stuff together. Okay. Activation energy is the energy required for a reaction to proceed. This is the hump in that diagram. It causes the reactant to become contorted or unstable. Try thinking about it as you've got a piece of flexible tubing, right? Pretty much activation energy essentially is you're bending it to the right shape so that it fits in the spot, right? I'm not sure if anybody's ever done any plumbing. You have to do a little bit of bending or a little bit. That's the activation energy until you can make that connection. That chemical bond can form, right? It causes the reactant to become contorted and unstable, which allows the bonds to be broken or made. This unstable state is called the transition state. Once the transition state, the reaction occurs very, very quickly. So if we look here, and we were to label this, where would the transition state be?
The hump.
Transition state would be up here, right? Now, even though this isn't, what type of reaction is this?
It's endothermic. Endergonic.
Endergonic, yep. Okay. Even though this is endergonic, once we get here, this happens quick. Okay. Once that rock gets to the top of the hill, it goes down really, really quickly. Okay. Once the transition state, the reaction occurs very, very quickly. Essentially, there's going to be a trend. It's in biology as well as in chemistry. Things want to be in their lowest energy state. Okay. It's kind of like you. What happens if you pass out? Where do you go? You hit the ground, right? That's our lowest energy state. Say what? Okay. Same thing within chemistry. It's going to go to the lowest energy state it can. All right. Yes, sir.
What if when we passed out, you started floating?
Then physics wouldn't happen. It'd be a thing anymore. All right. Heat energy is the main source of energy, activation energy in a cell. It helps the reactants reach their transition state. Endergonic or exergonic? Exergonic. Also says it tells you it's exergonic right there, right? As you can see here, do y'all know what catalyze means? Not quite. Do you know what catalyst does?
It gets it going.
Yes.
And then
Speeds it up.
Speeds it up.
Yeah.
A catalyst will speed up a reaction. What's a biological catalyst called? An enzyme. Very good, right? So you can see here, the activation catalysts work, and enzymes work by lowering this activation energy. So this can happen, 1, quicker, and 2, with less energy added. Helps reach that transition state more quickly. As a quick question, if your free energy is negative, is that endergonic or exergonic? Exergonic, okay? Because we're losing it, so we're going to be negative. We lost it, so we're losing it, okay? And if your free energy is positive, it is endergonic. Very good, right? Notice graph, the activation energy lower if catalyzed. Talk more about catalysts in section 6.5. Can you guess what catalysts 2 for reactions? What? Catalysts.
Do.
Yeah, it's probably due for reactions.
It speeds up.
Yeah, kind of lowers that activation energy. So, pretty good. Activation energy is why, for example, the roasting of iron happens slowly despite being spontaneous exergonic reaction. So this is kind of going to that thought that just because something is exergonic, it releases energy and it's spontaneous, it still might take a while. Because how long does it take for something to rust?
Like a day or two.
Yeah, right. Sometimes even longer, depending on what type of metal it is. Right? It still wants to go to that lowest energy state. That's what rust is. It's the low energy state of iron. But it will take time.
So can it do anything else after rust?
Depends what you add to it. Yeah. The breakdown of gasoline is another example of an exergonic reaction. Spark is required to provide the heat to exceed the activation energy. Once the reaction begins, though, there's enough heat released to drive additional reactions. So you can see here, this is just releasing the chemical energy in those organic molecules to transfer potential energy in the form of chemical energy to kinetic energy. Any questions on this? All right, how y'all like doing this way?
I like taking this on my phone.
Good,
So
yeah.
I don't lose and not have to worry about it in class.
I like the quizzes because it's easier to remember.
Yeah.
You know you have to do it.
All right, so checkpoint. What does A represent?
A is your activation energy.
Is it change-free energy? G, is it energy of activation without enzyme, or is it C, energy of activation
C. It's
with enzyme?
when it's with
B.
C. No, it's with.
It's B
It's C.
without.
It's C.
It's without it.
It's C
B.
with it.
So
No,
A,
without it. My bad.
okay.
B is without it because the enzyme will make it smaller.
See, it's really confusing because we're looking over here like B, A, and C, and it doesn't match up with these at all. All right, I'll accept it is the activation energy without an enzyme.
Oh.
So, because you see how it's taller? And then, so, let's see what the next question is. What does B represent?
C.
With enzyme.
Yeah, activation energy with an enzyme. It lowers activation energy. Very good.
Wait, that's what C represents? Okay.
Yeah, no, the correct answer is C.
Yeah, I know.
All right, and then what does C
It
represent?
changes for energy reaction.
Yeah, a change-free energy. Is this reaction exergonic or endergonic?
Extra.
Exergonic. For losing energy. Is it anabolic or catabolic?
Catabolic.
Catabolic, right? Yeah, we're releasing energy, breaking stuff down. All right, good deal.
This one's easy.
Sorry. All right, so what is energy?
The
Ability to
ability to do
The
work.
ability to do work. What's the difference between kinetic and potential?
Kinetic is potential and then potential.
Yeah, kinetic is motion, potential is stored. Now, it can be stored due to position, like gravitational potential, or it could be stored in chemical bonds. Chemical energy is a type of stored energy. What is free energy?
Energy available to do work.
Yeah, energy available to do work. How does it relate to activation energy?
Because don't you isn't free energy activation energy?
It requires activation energy.
That's why.
No. Because don't know it now. Your reaction requires free energy to actually start, doesn't it?
Keep in mind, when we talk about free energy, that's the energy available in the system. Okay? Usually we're going to be referring to it of our reactants and our products. Okay? The reason it's related to it is because activation energy has to be met before you can have a change in free energy. Right? You got to get up over here before you can start changing the energy of all the stuff. Because you can actually have times where you don't get enough activation energy and then it goes right back here. You don't have a change in free energy at all. Okay? Make sense?
So why is it there? Why is it free?
Can you expand that question some? So we'll say everything has energy, and it's just how much. Because this has more energy than this. Okay. And so within the biological systems, instead of it being gravitational, it's chemical. And so like every molecule or compound is going to have energy with it. It's just a question of how much. Okay. Does that provide a little more context?
Yeah,
Okay.
I guess I just don't understand why it was just there because is it just flowing around?
No, it's stored within the chemical bonds.
Oh,
okay. Think about free energy as the measurement of potential energy.
Okay.
In the chemical bonds.
Free energy.
Right. Does that make sense?
Yeah.
Right. Right. So if you have like a glucose molecule, it's got a lot more stored energy, so it has a lot more free energy. And then once it breaks down and you lose all that, it's got a lot less for energy, right? Okay. But delta G is just the change in energy. Good deal. What is the difference between endergonic and exergonic reactions?
Is endergonic like for in?
Okay, endergonic absorbs energy
Yeah.
or takes energy. The reactants have more energy than the products. Exergonic
It's really
releases energy. The reactants have.
less.
Wait, give me a second. Yeah. So endergonic, the reactants have less energy than the products. Exergonic, the reactants have more energy than the products. Okay. All right. Any questions?
No. I feel bad for my friend.
One.
She was stuck with her freshman. I could hear her yelling
Yeah.
the whole time.
Oh, she.
Yeah,
Was
she was
that
yelling.
bad?
Yes.
Yeah. You could hear her through the wall.
While they were taking the test.
No, after they were done. We were still taking ours.
Yeah, we
still.
were still taking ours.
Oh,
And
excuse
then
me.
you're finishing up the science section, and all you hear through the walls then. And then you heard yelling. You not understand what why?
Oh, you had a break too. They were
Really?
I went to the bathroom.
Thermodynamics. Dynamic means change. Thermo means you usually heat. In this same sense, we'll talk about it as energy. All right, the laws of thermodynamics. You'll get a leg up because you'll have this quiz tomorrow.
Oh.
Okay, so we're getting ahead, which it doesn't feel like we're cramming stuff in, does it?
No.
All right, no, good. Okay, good deal.
So
Mr. Rowell just put in laws and they already knew. They put thermodynamics.
Isn't it pretty crazy when it does that though?
Yeah.
It's like it knows. It's listening. All right, so thermodynamics. This is the study of energy and energy transfer. The first law states that total energy. Golly. Yes, absolutely.
You're probably tired.
Well, I did it last night. First law states total amount of energy in the universe is constant. Therefore, energy cannot be created or destroyed. I think on your CK12 stuff, I had it as energy cannot be created. The law of conservation of energy. Since that's the first law of thermodynamics, it's just a different name for it. Energy can neither be created nor destroyed. And again, thermodynamics is just the study of energy. Second law states that transfer of energy is not completely efficient.
Wait, isn't the first law the law of conservation of mass?
That is different.
Okay.
So we're talking thermodynamics is energy. We're just talking about energy, so we're dealing with those. How do y'all like it when they're all up there? Or do you prefer when it's bullet point? One at a time.
I like one at a time.
In all chemical reactions and all reactions, some energy is lost in a form that is unusable, such as heat energy. This results in increased entropy or disorder. Okay. So when you think of the opposite of order would be entropy. So if you have a system that has high entropy, that's high disorder, it will typically have low energy. Okay. I want you to think about this from like a chemistry or molecular standpoint. Because we're going to look at some pictures that looks at states of matter, and the reason that's important is because it kind of throws you off. To get to a higher state of matter, you have to add energy. So that makes sense. Okay, high entropy means high disorder, low energy. The example the book gives is this. Does it take a lot of work to clean up your room if it's real messy?
No.
So
Yes, it does.
if it's really messy,
If it's
yeah.
Legos, yeah.
Yeah, let's say, yeah, that's a great example. If you have a giant thing of Legos and they're out there, okay, does it take energy to put that Lego set together?
Yes.
Yeah.
Okay, right. That is entropy. You started out with a lot of entropy, a lot of disorder. You added energy to organization so that you had higher order and therefore higher energy. Okay, that makes sense? This is not time to be doing this. No, you cannot. You asked me that yesterday, and what did I say?
I forgot to answer that incident.
Yeah. Okay. You should be focusing on this, right? Listen, this is me being nice. I'm making it easier on you. If you take advantage of that, what happens to Mr. Rowell?
Then your shine stops.
Yeah, he becomes not nice, and you go back to Friday quizzes and have him take handwritten notes. Okay, right? The reason we have to do handwritten notes is to keep you engaged. Right? If you're not going to pay attention, we can go back to it. Yes, sir.
I'm too afraid to not be engaged. I would
So I'm
fail
gonna,
this class.
I did this part, right? And then when I go back to one of those things goes back. I think it's goes back.
He's so you're sleeping.
Okay, thank you.
That comes you can press enter a little bit too.
So entropy means disorder.
Yes, absolutely right. And the Lego example is great. And also, you're not doing well enough in this class. You're laying down.
Mr.Rowell.
Tough, right? And if you remember,
Yeah.
Yeah.
See, he makes kids cry since 2022.
arm straight. Okay.
Yeah,
So what'd you say?
Attention, though. I said it's
Oh, you can control attitude. Don't worry. Just ask my daughters. I'll make them control it. All right. Laws of thermodynamics. Living organisms must obtain the energy from their surroundings and transform it into usable energy to do work. How do organisms do this? Two processes.
Energon and what?
No, two processes.
Isn't it eating?
Yeah. What do we do with the food though? We
Metabolize it.
metabolize it with a process called.
Digestion.
Okay. Get it further down. Think about it at the molecular level.
Chewing.
No.
No, you too.
Starts with a C.
See,
Adam.
Cellular respiration. What's the other process that we can get energy? Photosynthesis, right? In some way, shape. So energy obtained from two sources, the sun and chemicals. But during the transfer of energy, some is lost as heat. Okay? So this is something, whenever energy is transferred, it doesn't matter what it is, some energy is going to be lost. Whether it's heat, whether it's some other type of energy. For example, if you throw a basketball on the floor, does it come back up to the same height?
Sometimes
No.
Yeah, it's going to be lower. One's gravity. Two is because also, what does a basketball make when it hits the floor? Sound. Okay, sound's a form of what? Energy, right? So we're changing this kinetic energy, and it's reverting back, and so it's being transferred from kinetic to, you remember from last year, to elastic. That basketball squeezes a little bit, and then it goes back to kinetic, but some of that energy is lost in the form of sound. There's probably also a little bit of heat there that gets generated. So even though it's a simple straight up and down, you are losing energy in some way, shape, or form, and energy is lost, right? That's the second law of thermodynamics. All right, so let's say we had a block of ice. This is water in its solid form, so that it has high structural order. This means the molecules cannot move very much and are in a fixed position. The temperature of the ice is 0. As a result, the entropy of the system is low. If you allow ice to melt at room temperature, what is the state of molecules in the liquid water now? How did the energy transfer take place? Is the entropy of the system higher or lower?
Is that how it is?
Yeah, this is kind of a sample network, right? So what's more organized, ice or water?
Ice.
Okay. So what's the opposite of order?
Entropy.
Entropy. So which one has more entropy?
The water.
Liquid water, right? Stuff's moving around. It's not a nice thing. The equivalent to you've got the Legos put together in a big block, or they're just dumped in your Lego buckets.
Or on my floor.
Or in your floor. No, floor is going to be the gas state. Okay. We heat the water to its boiling point. What happens to the entropy of the system when the water is heated?
Like a roller coaster.
It goes crazy, right? So as you can see here, we saw it's an increased entropy as those particles get less ordered and organized. All right, this is just another example. Just so you know, S is entropy. Yes, sir.
Okay, so when I know that ice expands when you freeze it.
Yes.
So is it like still like tightly packed, or is it more spread apart than other solids?
It won't. It will be more spread apart than water, but it will be more organized. And here's the deal. Because when you've got water molecules, I'm just going to draw water instead of doing the H2O for so if it says a liquid, they're just kind of every which way, right? And they can slide past each other. When it says a solid, it is super organized because you've got your oxygen molecule, and then this is how they will be organized, all of them. Because your hydrogen bonds will basically make sure,
That is taken.
yeah, that it's that this is the way it's organized. Okay, so it's like in a grid.
But it's more spread apart than liquid.
And the reason is, right. So this is the pattern you'll see roughly for the whole thing, because it organizes that way when it's a solid, but as a liquid,
It's just kind of like floating around.
yeah, they're just kind of floating around. I mean, they can get a little bit closer together, right? Because they're not dealing with those hydrogen bonds. It's just like as they start to get colder, those hydrogen bonds makes them stick in that certain position. Okay. Whereas other solids like fats, they just stack like this when they're solids, and then as liquids, they can kind of be every which way.
That's some modern art right there. So for a couple thousand.
Yeah, right. This is another example. Entropy increases as you go from solid to liquid to gas. Just entropy means disorder, lack of order. Okay. Also increases in the phase changes.
Oh, and that one, the water was pretty neat compared to the ice.
But there is still entropy in.
There's entropy in everything. Okay.
It's not as much.
You'll have entropy everywhere. There's no such thing as zero entropy.
What about absolute?
All right. There's no such realistic thing as zero entropy. Okay, because we haven't reached absolute zero yet. All right. Kids convert chemical energy, ice cream, to kinetic energy riding a bike, but heat energy is lost when plants utilize sunlight during photosynthesis. When you're utilizing energy, either playing basketball or anything, do you lose energy in the form of heat?
Yes.
Right. You're running, you're sweating, you're getting hot. Right. That is energy loss. Right.
Also, let's put some energy there.
Yeah. That'll work. Okay. Imagine a large colony with an elaborate nest. We'll say this is ants, connecting many tunnels and passageways. Now imagine that an earthquake shakes the ground and demolishes the nest. Did the ant nest have higher entropy before or after the earthquake?
After.
Before.
Entropy is disorder.
Oh.
Before because it's.
So after.
No, I'll say after because then it's like stacked again.
Yeah. So after the earthquake, everything's all messed up. It's not organized. Okay. So therefore, you're going to have higher entropy. Just think, organized means low entropy. Not organized means high entropy. They're opposites.
No, it's covered. Same with
It's already
viscosity.
evicted. They got evicted from their house.
What can the ants do to restore their nest close to its original amount of entropy?
They can build another nest.
They can build another nest. What do they have to add to it to do that?
Energy.
Energy. Okay. All right. Energy transfers take place constantly in everyday activities. Think of two scenarios like cooking on a stove and driving a car. Explain how the second law of thermodynamics applies to these two scenarios. Okay. Cooking on a stove. Where do we lose energy?
On heat.
Okay. Because is all of the energy from the
Burner.
burner going to the liquid we're trying to boil? Cook? No.
Going to the pot, going
Yeah.
to your atmosphere.
Yeah. What else can you ever heard stuff boil?
Yeah.
Right? Does it have sound?
Yeah.
Right? That's a type of energy. Right? You ever have anything catch on fire?
Yeah.
That's a release of energy. Right? In the form of heat, right? Yeah. Microwaves.
Yeah. What about
They
when you're
come off
standing
the-
above the stove and your face starts sweating? Is that
Then your face starts what?
sweating?
Sweating. I mean, it's still transferring, but you're still losing it. Okay. Give us 1 second. What about for driving a car?
You got sound energy, you got the stuff coming out the.
Friction.
Yeah. You also have excess heat.
Yeah.
Excess heat, right? It's not all getting converted to motion.
You
Oil.
accidentally touch your block when it's hot.
No.
I did that with my dad because it broke down on the side of the road. And he didn't tell me not to touch it, but I didn't think about it.
All right. So this is it. What is entropy?
Disorder.
It's disorder.
Yeah, it's amount of disorder. What's the difference between the first and second laws of thermodynamics? First law states.
Energy is constant.
Yeah, energy in the universe is constant. Energy can neither be created nor destroyed. Second law is
Energy is not being efficient.
yeah, energy transfer is not completely efficient. You will lose energy usually in the form of heat. All right, thank you very much. Okay, let's do seconds today. Drop it. Okay. Tomorrow we're gonna do ATP. Friday we'll probably try to do enzymes part 1. Yes, sir. Yes. Thank goodness we had class today.
That was an amazing day, bro.